Welcome students, I am Ravi Shankar. And in this fourth unit regarding electromagnetic induction and AC current, we are going to study about a phenomenon called to be self-induction and mutual induction. So for self-induction and mutual induction, first of all, we are going to consider the phenomenon called to be self-induction. So in order to study about this phenomenon, I am considering a coil of wire. And this coil of wire is said to have a number of turns. See, in general, we are calling this coil of wire as inductor. This coil of wire is called to be an inductor. So what is an inductor? When I am considering this coil of wire as an inductor, then I can say inductor is a device. Inductor is a device to store energy in magnetic field, or magnetic energy can be stored in magnetic field whenever there is a change in the current, whenever there is a change in the current flowing through the coil, change in the current flowing through it or flowing through the coil. So in general, we are saying that coil as inductor. What are some of the examples for that inductor? We can say a coil of wire or a linear coil of wire. That linear coil of wire otherwise called to be solenoid, or a circular coil of wire otherwise called to be toroid. These are some of the examples for inductor. So what is an inductor? Inductor is a coil of wire, maybe in the form of a linear one called a solenoid, or in the form of a circular one called to be an toroid. Is a device which is used to store magnetic energy, or we can store energy in magnetic field due to the change of current flowing through that coil. So in this inductor, we are going to study a phenomenon, and that phenomenon that we are going to study is called to be inductance. When you are studying about the phenomenon called to be inductance, this phenomenon is nothing but it is a property to generate or property to induce EMF due to what? Due to the change in the current flowing through it. Change in the current flowing through the coil. Okay, flowing through the coil. So whenever the current that is flowing through the coil varies or changes, an EMF is generated or developed in the coil, then we are calling it out as inductance. When you are considering this inductance, we can generally classify this inductance under two headings. One is called to be self-inductance, and another one is called to be mutual inductance. What is meant by self-inductance, and what do you mean by this mutual inductance? See, in order to explain this self-inductance, you consider a coil of wire, a single coil of wire. In this coil of wire, if the current that is passing through it, if the current passing through I changes, what happens? If the current flowing through that coil changes, an EMF is induced in the coil by itself, then that phenomenon is called to be self-induction. So this can be said that whenever the current through the coil changes, whenever the current through the coil varies, through the coil changes or through the coil varies, an EMF is generated in itself, generated or induced by itself, then we are saying it as self-induction. Then we are saying that phenomenon as self-induction. But in the same case of mutual inductance, you have to consider pair of coils, not a single coil. You have to consider a pair of coils. In any one of the coil, if you are supplying the current and the current changes, an EMF is generated or developed or induced in the neighboring coil, then that phenomenon we are calling it out as mutual inductance. In the first case, due to the change in current, the EMF is induced in the same coil. But in mutual inductance, whenever the current flows in one of the coil, produces an EMF in the other coil or in the neighboring coil. So how you can able to say this mutual inductance? We can say whenever the current through one coil changes, and EMF is induced or generated in what? In the neighboring coil or in the other coil, then we are calling that phenomenon as what? We are calling that phenomenon as mutual inductance, and it is called to be mutual induction. So we are going to study about these two phenomena in this topic. So first of all, in this we are considering about what? First of all, let us take about the coefficient of self-inductance or the self-induction. So initially we will be studying about self-induction. Okay, in order to study about the self-induction or self-inductance, or we can say it out as coefficient of self-inductance. Let us see. So in order to study about this self-induction, let us consider a coil of wire. Okay, let us take this coil of wire is having n turns in it. The coil of wire having n turns of coil. Now, what do you mean by this self-induction? First of all, let us define that. See, whenever the current that is flowing in this coil of wire varies, and EMF is induced in the coil by itself, then that phenomenon is called to be self-induction. First of all, let us define that. What I have defined, see, whenever there is a change, in the current passing through that coil, whenever there is a change in the current passing through the coil, and EMF is induced, in the coil by itself. So an EMF is induced in the coil by itself due to the change of current in that coil. That EMF, okay, that EMF is called as self-induced EMF, and the current is called as self-induced current, and we can call it out as self-induced current. The phenomenon is called as self-induction. This phenomenon or this property or phenomenon is known as or is called as self-induction, or you can say it out as self-inductance. Okay, so the self-induction or self-inductance is defined as the property of inducing an EMF in the coil by itself whenever the current flowing through that coil changes. Now let us obtain an equation. See, we are going to derive the equation. Here you are having a coil of wire with n turns. Let us consider a single coil. When the current is passing through that single coil, in that a magnetic field will be developed. The coil will have an area. So magnetic field multiplied with the area will develop an flux. So I am saying let phi b be the magnetic flux. Phi b be the magnetic flux linked with single turn of the coil. But there are how many number of turns? There are n number of turns. So what will be the total flux? So I am calculating the total flux linked with the coil is equal to linked with the coil. So total flux linked with the coil is the total number of turns multiplied with flux linked with each and every turn. So total flux linked is N into phi B. See how this flux is, we got the flux due to the supplied current. As the current that we are supplying in the coil of wire go on increases, then the flux linked will also go on increases. So therefore I am saying the total flux N into phi B is directly proportional to the current I that we are supplying. So I can simplify this. What is this? N into phi into B. N into phi into B is equal to, on removing this proportionality, I have to introduce a constant. And the constant that I am introducing here is capital L. L into I. So I am writing where this capital L is a constant known as the self-inductance of the coil, called to be self-inductance of the coil, or I can say it out as coefficient of what? Coefficient of self-inductance. Hope you should have understood what I am telling. So N phi is directly proportional to current I. The total flux N phi is equal to, on removing proportionality, I have to introduce a constant, and that constant introduced is called to be L in, is considered to be L. So L into I, where L is called to be coefficient of self-induction, or we can say it out as in general self-inductance. How to define this self-inductance then? So from this you calculate L. Therefore, the value of L is equal to N into phi B divided by the current I. How I can define this? Now consider, or you put the value of current I is equal to 1 ampere. If you are considering or putting the value of current I is equal to 1 ampere, then coefficient of self-inductance is equal to N into phi B. See, using this relation, I can able to define what? I can able to define coefficient of self-induction or self-inductance. How? See, from this equation, let us consider this as equation number 1. From this equation, I can state that, see, the coefficient of self-induction, coefficient of self-induction or inductance, or generally called to be self-inductance, is equal to, what is this equal? It is equal to N into phi B is total flux. So it's equal to total flux linked with the coil. Total flux linked with the coil. Eppo with the coil when a current of 1 ampere is passing through it. And a current of 1 ampere passing through it or passing through the coil. Or I can say this in reverse manner. When a current of 1 ampere passes through the coil, the coefficient of self-inductance is equal to the total flux that is linked with the coil of wire. So I can say the total flux linked with the coil of wire is equal to coefficient of self-inductance when a current of 1 ampere passing through it. This is one of the definition. One more definition is available with the help of Faraday's law. See what we have stated here. Whenever the current that is changing in the coil, then an EMF is induced. So I am writing that again. See, whenever the current I, whenever the current flowing through the coil, let us take like this, whenever the current flowing through the coil changes, an EMF is induced. An EMF is induced. Why an EMF is induced? When the current flowing through the coil changes, flux changes. Due to change in flux, an EMF is induced. So let us use Faraday's law. So I am saying, according to Faraday's law, what you have studied according to the Faraday's law, the EMF induced is equal to minus of d phi divided by dt. That is what we have studied. Here the phi is considered to be phi of B. But in your previous case, what we have written, but in the previous case, we have written as phi B is equal to N into phi B. And this N into phi B is equal to what we have written, it is equal to L into I. You just see the equation, above the equation number 1, N phi B equal to L into I. So therefore, this Faraday equation can be written as EMF E equal to minus of d divided by dt of total flux. Total flux is N into phi B. But N into phi B is equal to L into I. So I am writing this as minus of d divided by dt of, how I can write this as N into phi B? There I can return it as L into I. What is the function of the negative sign? The negative sign is used to indicate whether, or we can say the negative sign is used to indicate the direction of the EMF induced is always opposite to that of the cause, or opposite to that of the change in magnetic flux. So EMF induced is equal to minus of d by dt of L into I. So I can write EMF is equal to, take L to the outside, minus of L into di divided by dt. Therefore, what is L? So L is equal to minus of E divided by di divided by dt. See, from this equation also I can able to define what? From this equation also I can able to define the coefficient of self-induction or self-inductance. Let us see. Let us take this as equation number what? Take this equation as equation number 2. See, here you can write the negative sign indicates that. Here I can say the negative sign indicates that the EMF induced is in a direction opposite to that of the cause, or opposite to the change in flux. Opposite to the change in what? Opposite to the change in flux. Okay. See, from this how you can able to define the coefficient of self-induction. Here you consider, or you put di divided by dt is equal to 1 ampere in 1 second. That is, rate of change of current in the coil is 1 ampere in 1 second. Then what will happen to L? Then L will be equal to minus of E. So from this we can able to define the coefficient of self-inductance as, you see. So you can define like this. The coefficient of self-inductance is equal to minus of E. So equal to the opposing EMF is equal to the opposing EMF when the current in the coil, changes at a rate of 1 ampere in 1 second. So, or we can say if di by dt is equal to 1 ampere in 1 second, then the coefficient of self-induction is equal to the opposing EMF. Any difficulty? So this we are taking it as, or considering it as, the second definition for coefficient of self-induction or self-inductance. So how I can write this unit L? So what is the unit for inductance or unit for self-inductance? See, either it is self-inductance or mutual inductance, unit is same. So here we are calculating the unit for self-inductance. Usually the value of self-inductance L is measured in terms of an unit called to be Henry, represented as H. How you can write this in this equation? See, instead of L, I can substitute H equal to minus of, instead of E, EMF is measured in terms of an unit called to be volt, divided by di. I can write it out in terms of ampere divided by dt, time, in second. So how I can write Henry? Henry can be written as volt divided by ampere per second. How to simplify this? When I am simplifying, I can write like this: H is equal to volt. Take this second to the numerator. So volt second per ampere. This volt second per ampere is considered to be equal to Henry. How I can able to define unit self-inductance? What is meant by unit self-inductance? See, what do you mean by unit self-induction or inductance? Unit self-inductance means it is equal to 1 Henry of self-inductance. So how I can write this in this equation? You see, instead of H, I am putting 1 Henry equal to, instead of volt, I am putting 1 ampere. Instead of volt, I am putting 1 volt divided by, instead of current, I am putting 1 ampere, and instead of time, I am putting 1 second. So how I can define? See, 1 Henry of self-inductance is 1 Henry of self-inductance is in the coil, when a current of 1 ampere in 1 second, when a current of 1 ampere changes in a time of 1 second, then the opposing EMF induced is, because we are putting it as minus, so the opposing EMF induced is 1 volt. This is called to be 1 Henry. Or in the reverse manner, I can say, if the current in the coil changes at a rate of 1 ampere in 1 second, then the opposing EMF induced is 1 volt. Then the coefficient of self-inductance is equal to 1 Henry. Are you able to clear understood? So this is unit self-inductance called to be Henry. What is its dimension? See, dimension I can derive or I can write. If I am writing it, dimension is m L square t power minus 2 a power minus 2 is the dimension. If you want to derive, you can derive. See, for volt, here you are getting EMF, isn't it? Volt is for EMF. What is EMF? EMF is work done per unit charge. Then you know ampere for second. So simplify, you will be able to get. What is work done? Work done is m L square t power minus 2 by what is charge? Charge is current into time, A into T. So taking it to the numerator, instead of volt or EMF, we will be getting it as m L square t power minus 3 a power minus 1. Then you substitute in this equation. See what it is, volt divided by ampere per second. So volt divided by ampere by second, second will be taken to the numerator, so t power 1 divided by ampere. Ampere is A. Take this also to the numerator, you will be getting m L square. See, t power minus 3, here t power 1, it is t power minus 2. Take this A to the numerator, you get a power minus 2. So the dimensional formula is m L square t power minus 2 and a power minus 2. This we are calling it out as the dimensional formula, and we can say the unit as Henry, which is equal to 1 volt 1 second per ampere. See, there is also another unit, because from equation 1, we have defined it as L is equal to N into phi B divided by the current I. See, if it is N into phi B is measured in terms of what? Phi B is measured in terms of Weber. N represents turns. So I am writing Weber turns divided by what is current? Current, we are saying it is ampere. So in case of inductance, we can also write another unit represented as what? Represented as Weber turns by an ampere. This is another term of defining the unit for self-inductance or coefficient of self-inductance. So from this, we have stated about two equations, and from that two equations we can able to define what? From that two equations we can able to define the self-inductance or the coefficient of self-inductance. Hope you should have understood this. See, next to this in your book they have given an concept called to be what is the physical significance of self-inductance. Physical significance of self-inductance or self-induction. See, in order to study this, let us take like this a coil of wire, and this coil of wire is supplied with a current I. When you are supplying this current I around this coil, you are having a flux linked called to be phi b. Total number of turns available is n. So total flux linked is n into phi b. What happens whenever this current I changes? Let us take it increases. Whenever the current increases, then n into phi b also increases. So due to increase or due to change in the flux, an EMF is induced. This EMF induced is always in a direction opposite to that of the direction in which the current is supplied. See, isn't it? The EMF induced is always flowing in a direction opposite to EMF generated or EMF induced. Sorry, EMF induced is always flowing in direction opposite to direction of current, not EMF induced, opposite to direction of current or direction of flux. So let us consider it is opposite to direction of current. Since the EMF induced is opposite to the direction of current, this induced EMF will oppose the growth of the current in the circuit, growth of current in the coil or in the circuit. Am I correct? Are you clear? See, you are having a coil of wire. In that coil of wire, you are supplying a current. The current varies. Let us consider the current increases. When the current increases, then the flux linked with that coil also increases. When the flux linked with the coil increases, what happens? Due to change in flux, an EMF is induced in this coil. What will happen to the EMF? That EMF will be flowing in the coil in a direction opposite to the direction of the current. So this EMF won't allow the current to grow because this EMF is acting in a direction opposite to that of the growth of current. Similarly, let us consider the other phenomenon. That is, in the same experiment or in that same coil of wire, when the current is decreasing, you consider. When the current I decreases, what happens? N into phi b also decreases. When n into phi b decreases, what happens? EMF is induced in a direction opposite to the decrease in current, opposite to that direction of decrease in what? Direction of decrease in current. So EMF induced in a direction opposite to that of the direction of decrease of current, then that EMF won't allow the decrease of or decay of current in the circuit. So from this, what is your conclusion? Decay of current in the circuit. So what is the conclusion? Due to change in current, the EMF that was being induced in that coil of wire is opposing the change in the current. That is, it won't allow the current to grow. or it won't allow the current to decay immediately. Always it maintains an constant flow of electrical current. That we are calling it out as the physical significance. So the conclusion is the self-induced EMF or the self-induced current won't allow the current to grow, or it won't allow the current to decay immediately. For this, we can say an example. See, you might have seen the bulbs available in your automobiles, bulbs in, let us take like this, headlight lamps, headlight bulbs in your car or in your two-wheelers. So in a car or two-wheelers, even though if you are switching off the bulb, the filament alone will be glowing for some time and it will be gradually reducing it to zero. That phenomenon is due to, that function or that action is due to decrease in electrical current through the coil of wire. Similarly, when you are switching on, the bulb won't reach its brightness immediately. It will be taking some time to reach its maximum, because when there is a change in current, the opposing EMF will oppose the growth of the current. So the bulb won't reach its brightness immediately. It will be taking a small interval of time to reach its maximum. Similarly, when it is switched on, the bulb will be taking some time to get it completely decayed. So the bulb will be completely switched off after some time. This all due to the self-induced EMF in the coil of wire. Hope you should have understood this concept called to be coefficient of self-induction. The next topic that we have to study is, we have to consider the coefficient of self-inductance in a long coil of wire. In a long extended coil of wire is called to be solenoid. That we shall see in our next class. Until then, goodbye and thank you from Ravi Shankar. Thank you.